so we finally get to talk about ANOVA. I've been waiting all semester to talk about this, and now we get to. So hopefully you'll enjoy it as much as I do. ANOVA stands for Analysis of Variation or Variance. It can also be called Fisher's Analysis of Variation. Ronald Fisher introduced the term and proposed its formal analysis in 1918, and the first application was published in 1921, and then it became widely known after being included in his 1925 book. Here he is. You should think of it as a massive t-test for multiple groups. So it would not be smart if you had 5 groups to do, what's that, like 10 different or 20 different various combinations. But what ANOVA does is it just says, look at all these groups. Are there any groups that are different from other groups? And so if all the groups appear to come from the same parent distribution, it'll say, no, we don't see really any differences here. If even one group is different from the others, then ANOVA will say, something's different. And then you'll have to run follow-up tests to figure out which is which. Remember that when you're comparing numerical data against numerical data, very often linear regression is a useful tool. And when you're comparing categorical versus categorical, often it's chi-square. If you're comparing categorical versus numerical, usually you try ANOVA first. There are many, many other tests, but these are the 3 most commonly used first stab attempt at trying to solve a problem. Okay, please recall that when we were finding the standard deviation by hand, we used a similar process to what is listed below. We're going to calculate a mean, find deviations from the mean, square them, add them up, but luckily we don't have to continue. We don't have to divide by anything and take a square root. So we're not going to do that. But we're going to use the first half of that process. And we're going to use that process to calculate what's called the sum of squared total and the sum of squared within group, which are abbreviated as SS total and SSWG. So let's work on the first example. We're going to trace through some very simplistic examples. All the examples I'll ever give you by hand are very, very simplistic, not trying to make things difficult for you. Once you understand what's going on, then of course this is the kind of thing you feed into a computer. Okay, so let's say we have group X and group Y, or you can look at it as a combined group. If you calculate the sum of the squares of the deviations from the mean for the first group, the mean of the first group is 5, and so the deviations are -4, -2, 0, 2, and 4, and you square all that and add them up and get 40. And notice that the second group has data that are more tightly packed. Instead of 1, 3, 5, 7, 9, everything's more tightly packed. It's 6, 7, 8, 9, 10. And when you do the calculations there, you get a sum of squares of variations is 10. So you take the 40 and the 10 and you add them together and you get 50. Now for whatever reason StatCrunch calls this error. I don't like calling it error. It's a sum of squares within group. But if you're looking for it on StatCrunch, look for the word error. Now let's put all the data back together in one big set, and the mean of this data is 6.5, trust me. Okay, and then you take the differences and you square them and you add them all together, and again just trust me on that unless you want to retrace it, and you get 72.5. Okay, StatCrunch calls that total, which is fine by me. And what are these subscripts anyhow? Well, WG meant within group, total meant total, and now this one means between groups. For each group, we square the difference between the group mean and the grand mean. Maybe I forgot to tell you, this 6.5 here, this is the grand mean. You square the difference between the group mean and the grand mean, and then you multiply by the number of elements in the group. And right now this is very, very balanced because here we have exactly 5 elements in each data set, and so everything's going to look very, very balanced here. The 2 groups are perfectly balanced in terms of their weights. So each one gets a weight of 5, and so the sum of squares between groups is going to be 22.5 for these 2 data sets. StatCrunch calls this columns. Okay, well, because we put the groups in columns, I guess. Okay, now here's the shocking craziness. If you like the Pythagorean theorem, you're going to like this one because it's really the same. The sum of squares total is the sum of squares within group plus the sum of squares between group. And you're like, what? Where did that come from? Yeah, there's orthogonality under the hood. So here, this whole thing, sum of squares within group that we calculated this way, and this is sum of squared total that we calculated the same way, and then this process we use to calculate the sum of squares with between groups actually has this relationship for any sets of data that you will pick. Sum of squared total is sum of squared within group plus sum of squared between group, and that's just crazy. And of course you get like a p-value. This is the same p-value you would get if you did a t-test on these two groups. Okay, so it looks very much like what happened when we were adding variances. Yes, because we're essentially doing the same thing. It looks like the Pythagorean theorem. Yes, we're essentially doing the same thing. I don't see any triangles here. Yeah, neither do I, but they're there. Please understand that this is not true on a point-by-point basis. In other words, you cannot just take like one point, let's say this x here, and try to figure out like why this works. It only works in the aggregate. So for example, for the y data point of 9, you would get a squared deviation from the grand mean of 9 minus 6.5 squared, or 6.25. Your deviation from the group would be 1, so squaring it will give you 1. The component from the group to the grand mean is 1.5, which if you square it becomes 2.5. Notice 6.25 is not equal to 3.75, which you would get from adding these two pieces together. That's not how it works. It doesn't work for each data point. It only works in the aggregate, and that's why it's kind of magical. Okay, so if you want to work that out, you can try to figure out why it works. It's just like all the pluses and minuses balance out perfectly, but I'm not going to go further than that. I'll just leave it there. Okay, now getting to this thing called the F statistic. So now that we've done the hard work, actually finding the F statistic is pretty easy. If n is the number of points you have and k is the number of groups you have, then you just calculate these things. You just take sum of square between groups and divide by k minus 1, and sum of square within group, and you divide by m minus k, and you stack these things one on top of the other, and you get the F statistic. So let's do this for the exercise we just did. N is 10 because we had two groups of 5, so we had 10 points. We had two groups, so k is 2. Sum of squares between group divided by k minus 1 is just, if k is 2, then divide by 1 is really easy. And then we had sum of squares within group was 50, and then divide that by 8, which is n minus k. And you get 6.25, and then you stack the 22.5 on top of the 6.25, and you get a 3.6. Okay? So for degrees of freedom of 1, the numerator, degrees of freedom is 1 in the numerator and 8 in the denominator. And the F statistic is 3.6, which you can calculate on StatCrunch, or you can look up on that massive table. It's in Blackboard if you want it. But you can just look it up on StatCrunch also. And you're going to get a value of a p-value of 0.0943. Okay, this is showing you how to do it in StatCrunch. And you should just include the Tukey test in case you do reject the null hypothesis. If it's just two groups, it doesn't really matter, but if you have more than two groups, you want to tell which groups are causing the difference. Tukey, not Turkey. His name is not Turkey, it's Tukey. Okay, so he was an American mathematician, and he's famous for a lot of stuff. Okay, you can read about that. Second example. To build some intuition, let's have two groups with the same mean. And so I'm making the mean 5, so the combined group has a mean 5, each group has a mean of 5. But one group is sort of more stretched out. So what now? Well, you can actually ask StatCrunch to do this for you, and you can then just follow along and see if you agree with StatCrunch. So the sum of squares within group for sum of squares within group component from group X is the same as before, and since we already calculated that, you should remember is 40, or just go back and look in the notes. Now, the sum of the squares for the group Y is going to be 28. So the group Y is 2, 3, 4, 5, 6, 7, 8. And so you can see the calculations down below. So 9 plus 1 is 10. You've got two of them, that's 20, and 2 4s gives you 28. Okay, add that to the 40 and we've got 68, which is what StatCrunch said. So we're okay. I kind of want you to see both of these slides at the same time. But what's happening is because the mean is the same, maybe this is the best slide. The mean is the same for group X and Y and the combined group. And so the difference between these two guys is 0. Between group X's mean and the grand mean, the difference is 0. And between group Y and the grand mean, the difference is also 0. So then you're going to weight them by something, but who cares? A 0 times something is still 0. So the sum of squares between group is totally 0. And that's going to go on the numerator because you remember in this formula, this is what we're looking at. The numerator of this formula, the between groups, mean, square, whatever, but it doesn't matter. The k minus 1 is not 0, but SSBG is 0, so the whole F statistic is going to be 0. And that's just lovely because that's obviously going to give us a p-value of 1, because F statistic of 0 means I find absolutely no difference, not even a statistically insignificant difference, but no difference, absolutely no difference between the two groups because their means are the same. And that's why I'm getting a p-value of 1, which should seem reasonable. There is nothing less extreme. There's nothing less extreme. So all the more extremes add up to 100%, if you think about that. Okay, next example, example 3. I'm still going to use the same X group to save myself some work, but I'm going to make another copy of that and then slide it up by 100. So it's going to save me some calculation. So what we already know about group X is the sum of squares within groups is just 40. And so I'm going to have the same thing happening in group Y because it's the same thing just shifted. So the total sum of squares, that's the thing that StatCrunch calls errors, the sum of squares within group is just going to be 80. Okay? Now, the two groups are perfectly separated by 100 units. So the average is going to be, your mean is going to be 50 away. So this average for X is 5, average for Y is 105, and then right in the middle is going to be 55. So you're going to be from 5 to 55, the difference is 50, and from 55 to 105, the difference is 50. So we're going to square that and get 2500, and then you're going to multiply that by 10 because you're weighting it. And so that's exactly what StatCrunch said. So that's how you get the column value. And then the sum of squared total, now we know we can find it two different ways. We can just add sum of squared between group and sum of squared within group to get it, or we could recalculate it from scratch, which seems like a major headache, so let's just skip that step. But trust me, it would work. Okay, now this time the sum of squares between group, and therefore sum of squares mean of the squares between group is huge compared to MSWG, which is tiny. Okay, so now F statistic will be huge and highly significant. So notice the F statistic is like blown out of the water, and now the p-value is tiny. Well, that's obvious. Now if you just look at that, we have a whole bunch of points centered around 5 and a whole bunch of points centered around 105. They're clearly different. And the statistics backs us up. Okay, ANOVA is great for looking at lots of groups, so I'm going to do another experiment. I'm going to start with some bogus temperature data in Fahrenheit, and I'm going to slowly slide the values and squish them together so they become Celsius values. There's no deep reason for doing this. I just want to see when ANOVA triggers and says, hey, you have different distributions. So this is what the original underlying data looked like. I just generated it on StatCrunch. It's completely bogus. But the temperatures range from like, I don't know, 38 or something, 37, all the way up to 100 and some odd. I don't know. They could be temperatures. Okay, and this is what the transition is going to look like. I'm going to start with the temperatures in Fahrenheit and slowly slide them until they have become Celsius temperatures. This is what ANOVA tells us when I took all this, each one I had like 70 temperature values, right? And then I said, okay, what's the standard deviation and the mean and all that stuff. And so what ANOVA said is you definitely have some differences going on there. So ANOVA doesn't tell me which things are different from which things, but it says they're not all the same. Okay? So we did all this calculation, and oh my gosh, I would never do that by hand. This would be completely obnoxious. So what I want to know now is, what does Tukey say? Tukey says that if I compare my first, well, this is my Fahrenheit temperature, I can't really tell if there's a difference between D0 and D1 or not, but when I get to D2, I'm starting to get suspicious, and afterwards I'm pretty sure they're different. And you'll see this pattern keeps happening. Tukey has to do the pairwise comparisons of all the different groups. So let me go back to this picture here. So what Tukey is saying for any one of these guys, it really can't tell if the neighboring group is the same or not. But once you take 2 steps away, Tukey says, no, these guys are probably different. And then when you go 3 steps away, it says, okay, those guys are definitely different. Okay, so that is all you need. So that is the end. You can now do the last worksheet. And the last 2 slides are just to summarize like the whole semester in 2 slides. Okay, now that you've spent a whole semester in Stat 202, what can you do that you couldn't do before? So students come from different backgrounds, so I can't conclusively answer this, but I'm suspecting that many of you can do the things now that are bulleted below and probably couldn't do them before you entered the class. For example, figure out a good sample size for a poll you might wish to do. Come up with a good null and alternative hypothesis in a research setting. With some software, create a least squares regression line and make some meaningful statements about correlation. And you can add correlated or uncorrelated variables correctly, or at least if you don't know how to add correlated random variables correctly, you know well enough to avoid doing so. With software, you should be able to use chi-squared analysis correctly for categorical variables, and again with software, you should be able to use ANOVA correctly to tell if groups differ, and you should be able to apply Tukey's test or Bonferroni, there's other people too, but you should be able to apply some kind of test to tell which groups are causing the differences. What matters most to me is not exactly what you can recall or what you can forget 5 years from now. What matters most is what's left after you forget the precise course content. You have a better understanding now of statistical reasoning. You're less likely to be led astray by bogus arguments, and hopefully you're not intimidated by statistical sounding language. I hope that you have a vague memory of everything you once knew and that you can look it up again later if you need to know the details. That is my hope for you upon leaving this course. Now, go have fun with the homework.